All right, how about questions from your homework? Honestly, I don't remember which ones you had, but do you have any questions about them? Yes, just graph them and look on your calculator and tell what it is. A corner, a cusp, vertical tangent. Yes. So the difference in the cusp and the corner, the cusp will come in at kind of a curved angle and come to a point, and the corners are generally just sharp turns. Cusp approach the same thing, they just approach an undefined. You sure? Okay. It's like that is probably a corner. Like graph it. So 11 comes out to be a discontinuity, but just to show you, and you have to be you have to be in radian mode. So make sure in mode you're in radians and not degrees. And then you have to do a zoom trig on it. So let me show you. Somebody text me too tonight and remind me about metaphors tomorrow because I'll forget. Let's see. Inverse tangent, so second tan, x. And the second one is 1. But that's just plugging a hole there, it looks like. Let's see what the inverse tan looks like first. I'm going to make sure I'm in radians, and I am. I'm going to zoom 7 for trig. So what you're really looking at here is you know that there's a hole at 0 here, right? Because tangent, inverse tangent is undefined there. Y'all okay there? To know that it's and it tells you in the problem. Where am I? When x does not equal 0. Right? So this is when x is not 0. So if this equaled 0, it would be continuous because that's the value that it's approaching. So if I'd plugged that hole at 0, but it's saying leave a hole here and put a point at 1. So that's going to be a discontinuity. I don't know that this one would be considered a vertical tangent on this one. It's not quite flattened out enough. What else? Are y'all ready for some good stuff? I can't tell if y'all are just tired or didn't understand or it was just tired. Okay. Well then, let's talk about some rules for differentiation. Now we get to the good stuff. Been waiting on this all semester. What? Is it going to make you mad? Probably. We have 1, 2, 3, 4, 5 rules. 7 rules. I lied. 7 rules. Now, bless you. We can go through this one of 2 ways. I can just tell you what they are, or I can do the difference quotient for each one and show you how it equals this. No. Preston said no. You'll just believe me if I tell you that it's, if you do the difference quotient, you get the same. That was my plan, is I was like, I'm going to give them one and I'm going to say, okay, do the difference quotient, find the equation, and then I'm going to show you the shortcut. But I think that I'll just show you the shortcut and be done with it. Derivative of a constant. If you think about this one graphically, it makes sense. Okay, so if I do the derivative of some constant value, I'll call it C. What do you think that derivative would be? Remembering that derivative is just slope of a tan line. What kind of equation is a constant? What does that look like graph? What's the graph of a constant look like is what I'm trying to get at. A straight horizontal line. Agree or disagree? That's a constant. It's the graph of a constant. The slope is always the same, and it's always what? 0. The slope of any horizontal line. So the derivative of a constant is always 0. Does that make sense if I tell you that? So if I told you f of x equals 5, and I said, what is the derivative? What would you tell me? 0. Yeah, okay. What if I asked you what f prime of 10 is? Still 0. There's nothing to plug in. It's always 0. No matter what the x value is, it's always 0. Y'all sure you don't want me to show you the difference quotient, how it works? Okay. Thank you, Avery. The most excited you've been since we started class. Here's the fun one. This is the one that's really going to just tick you off. It's the power rule. If I take the derivative of some term that has an exponent here this way, I take this exponent and bring it around front, multiply it to the x's there, and reduce the power by 1. That looks kind of wordy, but let me show you what I'm talking about. In fact, let's use, yesterday we were looking at graphs, and every time you had a cubic graph, it looked like what when you did the derivative? A parabola, right? Well, if I use this, if f of x is x to the third, the derivative would be, by this rule, bring that around, 3x to the second. Now, if I plugged in the difference quotient and did x plus h minus f of x over h, and I simplified down, I would find out, in fact, that this is 3x squared. Y'all sure you don't want me to do it? Okay. We'll just do it this way. But we're going to talk about what to do when there's more. All right. How about if f of x, well, let me change the variable since I've already used that. What if g of x is x to the 36th power? What is g prime? First, tell me g prime of x. 36x to the 35th. Another way that this might be written, just so you recognize that, remember I told you there's all these different notations for derivatives. Some's dy dx, some is f prime or g prime, and others still might be d dx, and then the function the way it's written here. If you saw that y equals x to the, I don't know, 15th, and I said, what is dy dx? This is the same thing as this. It's just saying what's the derivative of y? Y is x to the 15th. So it would still be 15x to the 14th. Y'all okay there? Okay. Constant multiple. What number are we on? 3? And then we'll pull them all together. These remind me of like whenever you learned the exponent properties and we had like those 7 that we went through and then we put them all together. Constant multiple means I have some use you in your book. I'll just use you. This is a constant or a coefficient that sits in front, okay? What you can do as you do these is you can pull that around to the front and you can say, well, I'm going to do the constant in front times, then I do the derivative of whatever's left. And this is really, again, kind of wordy and weird looking when you do it like this, but it's saying if f of x is 2x to the fifth, and I want to find the derivative, well, that is just 2 times the derivative of x to the fifth, which is what? 5x to the fourth. So the derivative here would be 10x to the fourth. And most of the time we just skip that step and just multiply here and say that's 10x to the fourth. But that's the constant multiplier. Is it making sense so far? Mad easy. Mad easier than the difference quotient? Don't forget the difference quotient there, because it'll be tested, but you've already forgotten it that quick. All right, sum and difference rule. What are we on? 4. I'm glad you think it's mad easy. I like these because they do exactly what you think they would do. Like the constant still stays the constant out front, or the coefficient still stays the coefficient out front, multiplies. Sum and difference, same thing. If I take the derivative of two things added or subtracted together, I just do the derivative of them individually. We love using these in calculus. Well, what does this mean? This is essentially for polynomials and that kind of thing that I'm adding or subtracting. So here if I had f of x equals 8x cubed minus 12x plus 4x to the 30th minus 50. If I want to find the derivative here, I'm going to do each one individually. That's what this lets me do. This lets me say that I can split these up and find the derivative of each one. So what's the derivative of 8x cubed? How about 12x to the 6th? Multiply and lessen your exponent by 1. How about 4x to the 30th? How about 15? 0. It's constant. What do you think? Mad easy still? Yeah. Huh? Yeah. Okay. Easy to find at a point because you just plug the value in for x. We're going to get into a little bit funkier ones. Let me stop right here and do a little problem to show you how we're going to use this to do what we had been doing. Think about this for just a second, and then I'll remind me what number we're on. Let's say I have y equals x to the 4th minus 2x squared plus 2. And I say, does this have any horizontal tangents? What does that mean? where tangent is not undefined but close, go the other way, 0, right? Horizontal line slope is 0, so I want to know what I'm essentially asking here. What this means is, will y prime, or will the derivative of y ever equal 0? That's what it's saying. Will that happen? Well, now that I know all these rules, this is easy, right? We did this before, but we had that difference quotient. And this is the one where Henry said, well, I just looked at where the minimum was. I just looked at where the maximum was, which was right because that's a horizontal tangent. But if algebraically we're going through this, difference quotient would be really nasty, right? But if I know the derivative, what's the derivative here? 4x cubed minus 4x. Will that ever equal 0? Yeah, how do I solve that? Factor out of 4x, it leaves me x squared minus 1. That's a difference of 2 squares. So in fact, how many horizontal tangents does this graph have? 3. At 0, at 1, and at negative 1. Graphically, that makes sense if it's a quartic, right? Quartic might look something like this. Would it make sense that I would have 3 horizontal tangents on this one? 1, 2, 3. But how much quicker and easier was that, right? I just think that's beautiful. Maxes and mins of the graph. Because that's where we're going to do a whole section on analysis like that. But yes, you are correct. Y'all just, is everybody okay? Am I going too fast? Yep. That's correct. So if I needed the equation of the tan lines, or if I needed equation of, well, I guess equation of the tan lines. But yes, if I need this one, I have to plug to the original. One, two more. Okay. Should be good. I saved the hardest for last, the best for last. What number? 6? Product rule. This is where it starts getting sticky, but hopefully you do so many of these that you'll be able to do them in your sleep. So product rule, I'm multiplying essentially 2 functions together. Okay, so if I have the derivative of u times g. So this time, it's not, these aren't constants, they're not coefficients, okay? They could be entire functions. It could be a binomial and a trinomial multiplied together, something of the sort. So what you do for this one, you do the derivative of the first times the second plus the first times the derivative of the second. Do you always have to use this? No. With polynomials, a lot of times you could FOIL it out, get it to a polynomial, and then just use those exponent rules and do it there. Just a lot more room for mistakes. Sometimes you will encounter some that it will be a lot easier just to use the product rule. But just to show you how it works, let's say f of x equals x squared plus 1. And I'm asked to find the derivative of f. So I'm going to think about this one being u and this one being v. The order, of course, of these doesn't matter because addition is commutative. I can do it in any order that I want to. But just remember you have to take the derivative of one and multiply by the original other one, and then vice versa, and add them together. If I take the derivative of this, what do I get? 2x. Then I'm going to multiply it to this left alone. So x cubed plus 3. Now I take the first one and I do the derivative of the second. What's the derivative of the second one? 3x squared. And now I can clean it up a bit. If this is difficult to y'all, tell me, because we can do some more examples together and anything if it's a struggle. Had I FOILed that out in the beginning and then just did the derivative, I would have come back to the exact same thing. That's the derivative. Save the hardest one for last. Tonight we'll probably just practice. Tomorrow we'll start using them to write equations with handlines and stuff. Tonight we'll just practice with the rules. The quotient rule. You don't have to know the name of them. I just make some better notes if they're titled. All right, quotient rule. So this time I'm dividing, right? So I want the derivative. We'll use the same U and B. Here's what I'm going to do. I do the derivative of the top. So derivative of the top. I should probably do it the same way. Times the bottom minus the top times derivative of the bottom all over the bottom squared. Now, if it confuses you like this, this is the derivative of the top. So I'm going to do it like that so you know. Derivative of the top times the bottom minus top times derivative of the bottom all over bottom squared. The more you say it, the more it kind of sticks in your head. You just have to remember which one to start with, because this one, the order does matter because you're subtracting. So you always take the derivative of the top first. So very similar to the power rule, but I'm subtracting instead of adding, then dividing by the square. So let's do an example, and then I will shut up, I promise. That fly's still in here, Krill. Y'all try this one and see what happens. Find the derivative. Still got it? Maybe. All right, let's do it. Derivative of the top. What's the derivative of the top? 2x. Derivative of the top. Did you mess up already? Derivative of the top times the bottom minus. Now I go ahead and do the derivative of the bottom times the top, but you can switch that up. But whatever you want to do, minus 2x times this times the top, all over the bottom squared. Now, I'm probably going to leave that bottom just like that because factored form is perfectly acceptable and that's completely factored. The top, however, I'm probably going to clean up just a little bit. I got 2x cubed plus 2x minus 2x cubed plus 2x. I don't want to confuse anybody here either. I did the derivative of the bottom times the top instead of top times derivative of the bottom. Go ahead, do I need to what? Okay. These are gone, so I end up with 4x over x squared. Nope. Not unless you have to, yeah, sure. No, if it wasn't factored completely already, I might try to start. Yeah. This one, you might have done, they're very similar. The top and the bottom are very similar. They're just a sign difference. So the top is the subtraction. The bottom is the addition. All right, what do you think? Can you do a few? Hope you're okay. You look tired. Let's do